navigator in an Air Force aircraft carries a lot of responsibility on long-range flights. His knowledge and skill not only are an indispensable part of a flight operation, but they also can play a major role in making that flight a safe and comfortable one. One of the most important navigation techniques in today's high-performance aircraft is the use of the strong winds that often are to be found aloft. With proper navigation techniques, such winds can often mean a saving of fuel and valuable hours of flight time. With a knowledge of the upper wind field and proper in-flight soundings, a navigator can anticipate these strong wind currents, which are recognized the world over as jet streams, the superhighways of the sky. Jet streams are high-altitude currents of wind of great velocity, blowing in a general easterly direction around the globe at various latitudes. In the northern hemisphere, the existence of 3 of these has been well established: an intense wintertime Arctic jet stream, a strong, well-defined circumpolar current, and a persistent high-altitude subtropic stream. Recent weather studies have also disclosed similar jet streams in the southern hemisphere. In most of your flying, you will be concerned with a circumpolar jet, which is associated with the boundary or front between the cold polar air mass and the warm tropical air. These 2 air masses struggle for supremacy from season to season, pushing the front north or south. As the front moves, so does the jet stream high aloft. The jet winds also meander from day to day under the influence of changing conditions in the upper air. A cross-sectional view of the atmosphere shows that an air parcel undergoes a temperature drop with increase in altitude. The higher one goes, the colder it gets, until a region is reached where the temperature stabilizes. The lower region is called the troposphere and is where most weather takes place. Above it is the lower stratosphere. The boundary between the two is the tropopause. Because of heating by the sun, the tropical air mass extends much higher above the Earth's surface before it gives way to the stratosphere. The tropopause, however, does not slope evenly toward the pole, but has definite breaks along the polar front, where the cold air mass meets the warmer tropical air. As one air mass encroaches on the other, the sharp difference in temperatures along the boundary region supplies tremendous energy that drives this wind to high velocities, often in excess of 100 knot speeds, and sometimes approaching 300 knots. This is a jet stream. When the tropopauses are high because of the warm air mass temperatures, the jet winds are found at a considerable altitude, 40,000 feet or more. But when the mean temperature throughout the air masses is cold, the jet core is found at a comparatively low altitude, sometimes at 20 to 25,000 feet. This wintertime condition usually means a greater fracture in the tropopause. There are stronger temperature contrasts between the air masses. As a consequence, the jet velocities are much higher at this time of year. Generally speaking, a winter jet stream entering the North American continent from over the Pacific Ocean will start to swing southward, then veer into a northerly arc as it encounters warm maritime air. Ever-changing weather conditions, of course, modify this pattern greatly. But in the main, routine upper air analyses can give the navigator a pretty good indication as to the whereabouts of the jet stream. If you flew over the Atlantic with a jet stream, you ordinarily would find it losing intensity. This is due to the moderating effect the water has on the opposing air masses, which lose their jet driving force as the temperature contrast between them is lessened. Prevalent pressure systems, of course, influence the location and intensity of the stream in its transoceanic flow. Over the continent, the polar air has greater persistence, and since the temperature contrasts can be quite sharp, the jet winds here are usually stronger than those over large bodies of water. After long travel over land, the jet stream reaches its highest velocity over the eastern coast of Asia. Winds in this region have been authentically reported at nearly 300 knots. Once over the Pacific, the jet stream gradually loses intensity as the water moderates the temperature differences in the two air masses. Over North America, the continental polar influence again causes an acceleration that reaches its maximum over the eastern seaboard. Seen from a point above the North Pole, such a jet stream would completely encircle the globe. This is not literally true, however, since breaks occur where water influences and isolated weather conditions cause the streams to slow down and fade out. On the other hand, the jet stream may split into two or more currents under the influence of thermal conditions and various topographical features. As a navigator, you will discover that winds of 150 knots are not at all uncommon in the core of the jet. We have shown the jet stream as if it could be seen in the air. Viewed in cross-section, it might be likened to a long, flat tube. To depict this more clearly, we shall represent it as being greatly exaggerated in the vertical dimension. An examination of the wind structure shows that as one goes away from the core, the wind velocities fall off rapidly. Although there is no sharp line of demarcation between the jet winds and the general wind field, we have arbitrarily defined the jet stream boundaries as being where the winds are one-half that of the core. If we turn the wind stream so as to look directly downwind, it can be seen that the isotox, or lines of equal wind intensity, are bunched toward the polar side. The jet stream, as we have defined it here, may be several hundred miles across. The high-intensity winds at the core are to be found about 5,000 feet below the tropical tropopause and near the polar tropopause. The depth of the jet stream is often found to be 15 to 25,000 feet. The weather chart will normally show an ordinary cold front at the surface, with its characteristic temperature discontinuity near the ground. Flights in this region have recently disclosed similar temperature changes. Since they resemble those of the frontal zone at the surface, the name jet stream front can be applied. The characteristic bunching of isotox on the polar side and their dipping at the jet front where the temperature drops occur prove excellent guideposts to the jet stream. For instance, a navigator entering from the tropic side below the core would experience a gradual increase of wind velocities. Then, as his aircraft reached the jet front, he would get a sharp drop in temperature. If operational limitations permit, he could then turn with the winds and maneuver back through the jet front to the tropic side into the strongest winds. If his aircraft strayed away from this region, the navigator would have to be considerably higher to encounter winds of the same intensity away from the jet front. Another aircraft entering from the polar side would go through a much more rapid change in wind speeds, perhaps 3 times as fast in a given distance. As before, the navigator could use his knowledge of temperature shift at the jet front to enable him to position his aircraft in the strongest winds on the warm side of the front. Let's watch an experienced navigator as his aircraft encounters jet winds. We're on a flight from Biggs Air Force Base, Texas, to Dover Air Force Base, Delaware. The navigator has been advised that upper air conditions may result in a strong jet stream along this line. So his flight plan is to make good a course along here, with the expectation that he will have strong tailwinds along the greater part of his flight before he breaks out of the jet stream and goes on to his destination. Our navigator knows he is nearing the jet front because he's picking up an increasingly strong crosswind. Since he knows there'll be a change in temperature at the jet front, he carefully watches for it. If the lower temperature means he's crossed over into the polar air mass, then his drift meter should also show he's now in the region of slower winds. Check. Now to tell the pilot to alter onto a course paralleling the jet winds. Once on this course, the navigator again checks his temperature readings and drift meter repeatedly for the first indication that he's back on the tropic side of the jet front. After that, it's a matter of maintaining a constant temperature reading and minimum drift to keep the jet winds behind him. So our navigator used 2 basic indices, drift angle and temperature readings, to recognize the jet stream winds. If his aircraft can go higher and operational limitations permit it, the navigator may climb to the core where winds are most intense. Let's now consider another aircraft flying over water, where drift readings may not be possible. This aircraft uses D soundings in place of drift computations. A slight fall in D will be experienced in the tropic air until the aircraft reaches the jet front. Then there is a marked drop in D, as well as a fall-off in temperature. When an aircraft is flying with a jet stream, the navigator uses either D or drift, and both when possible, together with his temperature readings to stay in the high winds. Let's go from our cross-sectional view to one above the aircraft. If his heading takes him toward the warm air, there will be a left drift and a gradual increase in both temperature and D readings. If, on the other hand, the aircraft moves toward the polar side, the navigator will note a right drift and a drop in temperature and in D. As we have seen, a high-velocity jet stream acts much like a channel of fast-moving water in a river, with the highest winds in the core. As in a river, the regions between different velocities sometimes set up whirlpools or eddies. Aircraft going from one wind to another may encounter considerable turbulence. Although it usually is strongest on the polar side, turbulence may be found anywhere near the jet stream. Since there may be no clouds associated with this phenomenon, air crews have called it clear air turbulence. If the turbulence is severe and prolonged, the usual procedure is to reduce airspeed and decrease altitude. Since even strong turbulent patches usually are quite shallow, a minor altitude change may take an aircraft out of the turbulent air. When the navigator wants to leave a jet stream, he may simply change altitude. 5,000 to 10,000 feet can make a great difference in wind intensities. Or he may turn toward the polar air mass. If he leaves the jet stream at core level, he will encounter constant or even somewhat warmer temperatures in the stratosphere. D readings, on the other hand, are lower than in the tropic air. Navigating the jet streams is becoming an ever more routine operation. The jet stream's role in our aeronautical and scientific future cannot be minimized. Rocket experts have found that these powerful wind streams exert great influences on missile trajectories. So even man's quest for outer space must take into account these raging currents, the jet streams.